All right, so it's my pleasure to introduce Gil Cavalcanti from Utrecht University, who will speak to us today about T-duality with fixed points. So please, whenever you're ready.
Okay, well, thanks very much for the invitation to be here. It's nice to see you guys. I expected a small group of people in a room, so it's nice to see people from all over the place attending. I'll talk about T-duality fixed points. This is based on a paper with Aldo Witte, and he is currently looking for jobs. So if you have a job and you like the talk to him. So before I start, let's see what's the first slide. So that's one thing. Let's see. Yeah, no, it's okay. Before I start with the T-duality fixed points, I just want to play something here. But I wonder if when I play, if you guys get to hear the sound. So I'll just see here, because sometimes it doesn't get the sound from the computer in the. I don't know. I like this one. So I like it so much that I put here today. They have a race. There's a decathlon or something, and there's a tie, and whoever wins the race, their team wins the whole thing. And let's see what happens.
We don't hear it though, but
Yeah, we don't have the sound, I guess. But you can narrate for us.
Anyway, I think, of course, this is not about it, but I think it illustrates an interesting point that can happen with mathematicians who decide to do something related to physics, and it may be happening today. In that we pick something that we think we understand and start going with it, and at some point we take a tangent and we go for it, and yeah, like we feel like they're winning the whole thing, but maybe it doesn't really connect to what we started with. So that's a disclaimer. I'm a mathematician doing mathematics inspired by physics, and it's unclear to me if it connects to physics at all, what I'm going to say. So take everything with a grain of salt. So if you start asking, but is it really physics? Then I don't know. That's the kind of the fair answer. But then is it string theory physics? I also do not know. And another question you could have, which I think might have a better answer, would be, is there some sort of physics string theory-like concept that would match what I'm talking about? There the answer is probably yes. But let's go with it. So I'd like to talk about T-duality with fixed points. So first, just a little bit, very brief history of T-duality, and from somebody who doesn't know the topic. So feel free to correct me at any point. When I check the Wikipedia, what they tell me is that it was first observed by Bala Satyapalan. They say it's a very not very well-known paper. It's like, of course, it's cited in Wikipedia, so it's well-known enough, but doesn't get many citations, has like 100 citations or something. And itself, the paper is very simple because it just does this thing of taking a model with a target, the circle, and he observes that in his model, if you were to flip two things at the same time, namely invert the radii, so turn radius to 1/radius, and swap the winding and the momentum, you get the same model. So that's what he observes. Like there is some sort of symmetry in the model that is the whole thing is invariant under these two simultaneous changes. And one thing that I hear sometimes is also the swapping of winding and momentum would be something like exchanging of tangent and cotangent directions. That's something that people made sense of. But yeah, so that's 1987. That was like the first time that's recorded. Even if you read the paper, he says that he had talked to people, and apparently it was up in the air, but he does not cite any specific reference for this. So it might be something that just was had been observed and nobody put it down on paper before. Still in 1987, people made it a bit more precise. So there was Buscher and I guess Martin Rocek was a supervisor. They kind of go from just this inversion of radii to something a bit more complicated. So they pick one of these, what nowadays called generalized metrics. So it's a metric and a B field together, and figure out what the T-dual metric is using physical arguments. And one thing that you notice is that the G0 here, which is something like the radius of the original circle, gets inverted in the T-dual metric. So there's this inversion of radii that Satya Palan had found, but also things like the B field can come in and influence the new metric, and the new metric, the old metric, can come in and influence the B field, for example. So there is a swap, not just of inversion of radii, but once you have more, these fields have more tensors, more parts to them. There's more of a complicated interchange of the different terms. So that was Buscher, and I think that's a lot of physicists think that this is like when we understood T-duality better. So a lot of people refer to the Buscher rules as like the beginning of T-duality. In the 90s, work continued, and a few people worked on this. A few names that go often are Chris Hole, Rocek, and Verlinde. But there are other people. It's just I didn't get more names, but it's certainly something that has been well studied. And I'm always surprised because when you hear about T-duality, one that's not that old. I always thought it had been there forever, but it's from the 80s. So like for me, that feels already my lifetime. And you always hear that people think that T-duality should be something that is like your physical model should be invariant under T-duality. So somehow the work that was done in the 90s was so settling that nowadays we think that the physical model should be invariant under diffeomorphisms, gauge transformations, and T-duality. So, and every now and then I'm still surprised when people figure out, like I think Mario not so long ago had a paper telling us how to do T-duality for heterotic string. And somehow all these names are so old, and yet the paper that says how to do it is quite recent. So it's sometimes there is this disconnect. I think something's very old, and yet this is still ongoing. From my point of view, one interesting, or the interesting development, that brought mathematics into the whole thing, was this thing that they call topological T-duality. That was from 2003, in which instead of being this thing that Buscher had, which is a bit like a local coordinate, so you have a trivialization and describe how different fields transform in a trivialization, they had a more global description, which included this thing that the topology of the space changes depending on the presence of an H-flux. So you exchange the H-flux in one side with the curvature for the circle bundle on the other side. So that was like a very interesting thing that called attention of many people. They showed that the T-duals exist, at least for circle bundles, and they studied also when they exist for torus bundles, and went on to study like what's the relation between T-dual spaces, and their answer was that T-dual spaces have isomorphic twisted cohomology and isomorphic twisted K-theory. So they are not just T-dual spaces, but there is a relation between some basic things that you can do about these spaces. One thing that is interesting that in this work of Balknach, Efsling, and Matai, they often refer to the T-dual bundle, and somehow the way they construct it is if like there is just this one here, it's unique, and yet this question of uniqueness was picked up in 2005 by Bunke and Schick, and essentially T-duals are not unique. You always have a choice. You have at least a choice of sign. So you could pick the plus the Chern class or minus the Chern class. So there's some freedom there. But technically, you can even scale the Chern class and pick a bundle that is a multiple of the original one. So like there's several non-isomorphic, non-diffeomorphic manifolds which can be T-dual to a given one. And there was at least one obvious thing that everything's done using diffeomorphisms, using using differential forms. So torsion is missing in the picture that these guys give. So that the existence of torsion is also a source of non-uniqueness. That was something that was studied in some detail by Bunke and Schick in 2005. And in 2005, and I guess the actual paper only came out 6 years later, we observed that we brought current algebroids to the picture, observed that this whole T-duality thing was very well, could be very well described mathematically using current algebroids, so T plus T star. That was something that had been current algebroids had been around since the 90s, but somehow they got revived in 2003 when Hitchin came up with generalized complex geometry. And what we observed in 2005 is that T-duality was a symmetry of the space where these generalized complex structures live, so T plus T star. And the type of map you got was this type of map that picks a vector, and here is supposed to be the vertical direction, so like the circle action direction. Here you have a basic form and a corresponding connection term that pairs non-zero with the action vector. And what T-duality map does is pick these elements of T plus T star on this side and give me something T plus T star on the other side, but flipping the tangent and cotangent directions, just like the physicists had been saying for a long time. But let's say mathematics did not have a language to understand that kind of a terminology. So now we could understand it, and it was just this flipping of T plus T, of tangent and cotangent directions in T plus T star. But that was an isomorphism of current algebroids. So every time you have a structure defined here, you can just transport it to a structure defined here, as long as it's just defined in terms of current algebroid data. So that was like I don't know, a very clean mathematical description that pairs well with the Balknecht, Efsling, and Mattei description of what T-duality does, and allowed us to really just transport structures from one side to the other and relate spaces with different structures. And one thing that was also nice about this description of Balknecht, Efsling, and Mattei is that to do T-duality, you start just with a manifold, which is a circle bundle, and then you do T-duality. You don't need any further structure in your manifold besides the fact that it's a circle bundle, so you need a circle action. Everything else is the stuff that you put on top and requires to be S1 invariant, and you can try to transport and see what it becomes on the other side. But you don't need to have a whole bunch of structure in the original manifold to be able to do T-duality. So T-duality happens to the manifold, and all the structures come afterwards. So there are many questions that came after these things have been settled. So up to this point, I would say that up to this point here, where we've got the isomorphism of current algebroids, the story is kind of quite neat, and it's a bit of a blueprint of how I personally would like T-duality story to always go. Of course, it doesn't always go like that, but it's very clean. It's supposed to be a geometric duality, and now we actually know how to relate spaces, how to transport structures between spaces, and where these structures should live, namely current algebroids. But you can start asking, what if you have structures which are not invariant? Can I transport them via T-duality? So this is something that Mattei and his collaborators tried to do. So they came up with the idea of exotic current algebroids. I don't fully understand them, but what I understand is that the idea is that if you could average things, you could transport the average, and then you can start tensoring the line bundle over and over and transport different averages, which should correspond to some sort of Fourier modes. So in the end, you get a sequence of things on the other side. So it's not geometric anymore. So the idea that you can pick a structure on one side and get a similar structure on the other side is missing in this non-invariant setup. If the circle action is not free, it's something that Bunke and Schick also tried to tackle. And they tried the case where you have discrete isotropy. And the idea is that because you have this thing that the circle, R goes to 1 over R, so that this inversion of the radii, if suddenly we have isotropy, that means that that circle becomes smaller, I think. Right, so you get close, like the circle of isotropy closes faster than the nearby ones. You say the circle in the center circle would say close when you get halfway through, that would be isotropy Z2, while all the nearby ones would take you a whole extra half a circle to close. So when I have a non-free circle action, I have a circle. The circles with the orbits that have isotropy are smaller than the nearby orbits. So when you do T-duality, they become bigger, but like it's immediately bigger, not just a little bit bigger. So you have a whole bunch of circles and suddenly one that's like 3 times the size or 2 times the size. So these are not manifolds anymore. And then they have the theory of Orbi spaces, which is precisely the type of spaces that should have this kind of behavior. And one side you would have like an orbifold. So this would be like the dual to an orbifold, because orbifold they have quotients. This one somehow some points have extra long things. But again, it fails to have this geometric feature that if you have a structure on one side, you don't transport it to the other side, because these Orbi spaces, like what's going on in the central fibers, the singular fibers, things are a little bit funny. And what if there are fixed points? And that's the point that I realized that I should make a drawing. And I got my computer instead of my tablet. But so I guess you guys have to just look at my hands. I should have done something else. So like, let's imagine, so now it's in my hands here. So imagine I have a sphere and I'm just acting on it by rotation. Then I have a collection of circles that as I approach the North Pole or the South Pole, those circles are becoming smaller and smaller. No matter which metric I pick, there's a sense they are becoming smaller. So if I try to do T-duality, just from this R going to 1 over R means that the T-dual circles will become every time bigger. So it becomes a bit of like it's not even a hyperboloid, because it goes just from -1 to 1. So like it's the base, which is just the interval from -1 to 1, is the same, except that on this side here, as I reach -1 or 1, you have to, the radius has to go into infinity. So it becomes something that has this flat planes. It becomes like a asymptotic to planes. And you can actually go and compute like distances and so on, and these spaces are not complete if you just try to do that. And there's no way, like at first, this R going to 1 over R forces you to do this. There's no way around that at first. And you start getting incomplete metrics. And there doesn't seem to be a nice way to like compactify it, because the radius is going to infinity. So what do people do when there are fixed points like that? So you start hearing like more structure comes in, so that you can describe the T-dual. So you may hear like the T-dual of a sphere involves a superpotential and some holomorphic map to the plane. Landau-Ginzburg models are words that come in, and sometimes non-commutative geometry is also something that you hear in this context. So like the presence of fixed points spoils a lot of the picture we had before, and it really how can I say, it like before it was manifold gets T-dualized to manifold, and the structures come later. Here, to kind of make sense of it, you have to put a whole bunch of structures on the manifold to start with, just to be able to talk about the T-dual, because it starts to become a different type of object than what you started with. So that's like it's not a good parallel to what we first had. So the question is like, can I have T-duality with fixed points that mirrors more the first thing that I was talking about, just usual T-duality? So what I would like to propose today is that, yes, it's possible. We have to kind of do something to get there, so you won't get it for free. But I'll first tell you a little bit about just what T-duality is, like be a bit more precise about how it's done. I'll tell you a little bit about what the ingredients are that will allow us to deal with fixed points, namely log tangent spaces. And then I'll relate log tangent spaces to torus actions. And eventually, once I have all these things in place, I can talk about the duality of fixed points. And I'll finish just with what I call the lifting question. So the idea is that log tangent spaces are special types of Lie algebroids over your manifold. And one question that we may or may not be aware of is that sometimes we may want to lift geometric structures on a manifold to a Lie algebroid over that manifold. And sometimes we do that without thinking. Sometimes it's very obvious that we have to think about it, and we are doing a lifting question. So I'd like to talk about these 5 topics today, 5 points today. So let's go through T-duality, unless you guys have questions about the introduction. Okay, so I'll continue. So T-duality, the original one, Balknecht, Ebsling, and Matai, and T plus T star T-duality. So 2 principal torus bundles are T-dual. So like the torus bundles, they have already like underlying, they come equipped with closed 3 forms. So E has a closed 3 form H, and E tilde has a closed 3 form H tilde. And they are T-dual if when you pull back to this fiber product, which we also call the correspondence space, they are actually exact, their difference is exact. So their field strength cancels out, as the physicists say. So df is equal to h minus h tilde. And on top of that, we require that this f is non-degenerate. I pick one vector which is tangent to the first, like this is supposed to be the Lie algebra of the first torus on the E side. This is supposed to be the Lie algebra of the second torus on the E tilde side. And I can pick this f and pair with the infinitesimal generators of the action, and it should be a non-degenerate map. So if I have these two conditions, then I say that E and E tilde are T-dual to each other. And you can have many T-duals to a given space if you follow this definition. They don't have to be unique. What Balknecht, Evslin, and Matai did was to show that if you have a circle bundle, so one of the things they did was to prove existence. So if you have a circle bundle and you pick a connection to the circle bundle, say with curvature C, so this, like technically the C is 1/2I curvature type of thing. I'll drop my i's in the 2 pi's. So it's just curvature C. In H, assume that is also an integral class, so you can always write, because it's invariant, you can always write as some component that has like theta directions in the basic form. Then because H is closed, the C tilde is also closed, and if H was integral, the C tilde is also integral, so I can use the C tilde to define a new circle bundle. So I pick a new circle bundle whose curvature is going to be the C tilde that we had before. So that's how it's uniquely defined, like it is defined by that property, and it's uniquely defined modulo torsion. And only tilde you can write the form, this one here, H tilde equals to this. And then you pick the F equals to theta tilde wedge theta. And then if you do this, you do get the T-duality, like this E and E tilde are related by T-duality. And this is kind of really what a lot of people think about when they're doing T-duality. This is a specific set of choices that you pick this E tilde, you pick this H tilde, and you pick this F. Often they talk about the Poincare line bundle. So there's a specific way to get T-duals, and if you have more circles, you kind of just repeat it over. And there's a condition that the H should have this kind of expression. You should not have θ1 wedge θ2 if you have like a torus action instead of a circle action. You should not have θ1 wedge θ2 appearing in H. It should just really be θ1 with some basic form, θ2 another basic form, and so on. And then you can use that collection of basic forms to define the Chern classes of the next bundle. And then you produce the tilde with a corresponding H tilde, and you get a corresponding torus bundle also by pairing the appropriate theta's. But yeah, so essentially saying, if you give me a circle bundle, I can always find a T-dual space for you, and I have to make choices to do that. So I think this one is already kind of mentioned. If I have S1 acting on S2 fixing the north and south pole, or if you have something a bit more interesting like T2 acting on CP2 with non-trivial isotropy, like by rotating the coordinates, you get isotropy along the 3 lines. So if the first circle rotates Z1 and the second circle rotates Z2, then you get the coordinate axes are fixed and the line at infinity is also fixed. So if you try to T-dualize this, the T-dual would have this blowing up behavior where you have fixed points in the original action. And one thing that before we started this project, I actually did not know, and I had never heard anybody talking about, like in this example of S1 acting on S2 or T2 acting on CP2. Like what did I do in T-duality the first time around, or what did Balknecht, Evslin, and Matai did in T-duality in the first time around? They picked a connection, they looked at the curvature, and used that to produce the new guy. And I actually have never heard of a connection for the T2 action on CP2. And if you ask me off the bat, like what's the curvature of what should be the curvature of such a connection for the standard T2 action, the toric CP2? I'll not really know what the answer is. What's the curvature? So like, even though CP2 doesn't have a degree 3 form, so that at least is clear. We are supposed to be changing curvature with the H, the 3 form, and I don't even know what I should think of as the curvature of T2 acting on CP2. And I would like to take, so to be able to kind of repeat what I did before, I have to kind of say a little bit about what is the meaning of having a connection and what is the curvature of the connection, in this case of actions with fixed points. And the idea is that the geometry of the fixed point set should be taken into account when I try to get that answer. So how do we take the geometry of the fixed point set into account? The answer is log tangent spaces. So there are three versions of log tangent spaces. I'll go through all the three of them. The third one is the one that I eventually wanted to consider, but they're all important, and they all play together in this context. So I'll just go through all of it. So like the first case is the simplest one. It's called the B tangent bundle. And here I talk about having a manifold with boundary. But technically, you don't. I'll keep on writing manifold with boundary, but technically it doesn't have to be a boundary, it just has to be a codimension one submanifold. Once you have that, you can consider all the vector fields tangent to the boundary. So if, say, the boundary is parameterized like by x1 equals to 0, so the x1 equals to 0 cuts out the boundary, then you can actually figure out which vector fields are tangent to the boundary, and you'd have the ddx2, ddxn in a coordinate chart would be all tangent to the boundary, and x1, because x1 is supposed to be the coordinate that's transverse to the boundary, that doesn't work. But if I multiply by x1, then this one vanishes along the boundary, so that's also fine. And these guys generates all the vector fields tangent to the boundary. So if you want to look at vector fields tangent to the boundary, the sheaf of vector fields tangent to the boundary is generated by this. So it's a locally free sheaf. So it gives rise to a vector bundle. You can take Lie brackets of things like this. It's again something of this form. So it's a Lie algebroid. It's called the real log tangent space, or the B tangent space. I'll denote it by A del M. And whenever you have a Lie algebroid, you can look at forms. So here, for example, the Lie algebroid forms would have this kind of expression. And the idea is that from the Lie algebroid point of view, this guy here is just one of the generators. So like this is a frame for the Lie algebroid, including at x1 equals 0, so just a formal symbol. And similarly, this guy here is just supposed to be the dual element to this one here. So it's even though it looks singular, it's only singular if you try to think of it as a smooth one form on the manifold. As far as Lie algebroids go, this is just the denotation for the dual element to this section here. So they are all smoothly defined. It's not a formal computation that I'm doing, even though the symbols are formal manipulations. This is actually just like a co-frame for my Lie algebroid. This kind something that maybe at first, if first time you hear, maybe it's a little weird, but if you've heard it a few times, you think that I'm just wasting your time here. This construction also works if M has corners. It doesn't have to have just one smooth boundary. So for example, in the case I just mentioned of having, say, CP2 with the torus acting on it, if we look at what the quotient is, it's supposed to be a triangle. It's like the image of the moment map. So it's a manifold with corners. So if I want to think of the quotient of CP2 by the action of the torus, the resulting manifold is a manifold with corners. So this is the world in which this kind of object lives. So I can talk about the log tangent bundle of that triangle. Is this clear? Were you guys familiar with this already, hopefully? Same thing can be repeated if you have a complex manifold. So if you have a codimension one complex submanifold, you can look at all the vector fields, the holomorphic vector fields, which preserve the holomorphic ideal. And that would be just like the same thing that I just did before, except that instead of having real coordinates, I can have complex coordinates. But you can also just look at the complex vector fields which preserve the holomorphic ideal, and that is itself also a locally free sheaf. So if I had done holomorphically only, I would get these guys here. But if I just look at the smooth vector fields which preserve the ideal generated by, say, the function z1, so that the codimension complex submanifold is cut out by z1 equals to 0 in this coordinate chart, then the smooth vector fields which preserve the ideal would be these guys here. There is a lack of symmetry, so that's something that we didn't have in the real case. Because here I have z1 dz1, but dz1 bar just preserved, like dz1 bar of z1 is just 0. So there's a lack of symmetry between z1 and z1 bar. So this is really just a complex Lie algebroid at the moment. And even though I start telling you about having a complex manifold with a codimension one complex submanifold, you don't really need any of that. All you need is the holomorphic ideal. Once you have a holomorphic ideal defining a real codimension two submanifold, so like if you have a candidate for the function z1, or the ideal generated by the function z1, you can already look at these vector fields preserving that ideal, and you get already the algebroid. So it's even though I start talking about complex manifolds, this is more general than complex geometry. It happens already just in real manifolds. You don't need a complex structure. And once you do this, this guy here is supposed to be the complex log tangent bundle, and it has a dual again, which has a de Rham cohomology and everything. So these are the generators, and here you see like one, so to speak, singular looking generator, which is the dual to this vanishing vector, but from the Lie algebroid, again, all makes sense. They always move things. And similar to the original case, which works in manifolds with corners, this thing also works if D has transverse self-intersection. So if I was in CP2 and I look at the 3 lines, so the 2 coordinate planes and the line at infinity, I can actually talk about a log tangent space for CP2 with those 3 lines as distinguished by this in this process. So I change the tangent space into a log tangent space, which would have the singular generators that are singular along those lines. But there is this distinction that dz1 bar appears and dz doesn't. So like there's a lack of symmetry. It's not. It's really a complex Lie algebroid. So the next one. So yeah, that's part of it. It doesn't have to be a complex manifold. It can be just a usual manifold with somehow these holomorphic ideals. So the next one is try to kind of bring back some symmetry between dz1 and dz1 bar to make it into a real object. And what we do here, maybe this one is a bit more complicated, which is we start with a manifold and a codimension 2 submanifold again. And for this codimension 2 submanifold, you look for, you assume that you're given a principal ideal that's locally generated by a Morse-Bott function that vanishes along this submanifold. So the idea that you should have in mind is that in the previous case here, I had Z1 was the function defining D, and now I have, like, I don't want to make a distinction between Z1 and Z1 bar, so I just have the product, Z1 times Z1 bar. That would be a Morse-Bott function that vanishes precisely along that submanifold that we're looking at. Once the ideal is Z1, Z1 bar, then I see that if I want to look at the vector fields which preserve the ideal, I'll get both the Z1, dZ1, and Z1 bar, dZ1 bar. So I got my symmetry back because Z1 times Z1 bar is a real function again. And I can actually go into real coordinates and get a corresponding real Lie algebroid. So this guy here in principle is a complex vector bundle, but you see there is a complex conjugation because each one of these guys has a corresponding complex element there. So there's actually a real underlying vector bundle here. And if we write Z1 in polar coordinates, the generators would be RDDR, so the Euler vector field, dd theta, which rotates, and the remaining coordinates that are tangents, the submanifold D. And the choice of which one is Z and which one is Z bar is like the choice of polar coordinates. It really influences which direction theta goes. So if I had somehow, like if I have Z1 times Z1 bar, I cannot really decide which one I should call complex coordinate because I don't have an underlying complex structure to tell me which one is the preferred one. Then the difference between choosing one or the other would be that what I call dd theta would change sign. So the complex circle would rotate the other way around. But anyway, locally I have a Lie algebroid, and all I need is that locally I can choose Z1, Z1 bar, and even if I go from one patch to another, I don't have to pair Z1 with Z1 and Z1 bar with Z1 bar. So I can have coordinate charts that just send Z1 bar to say W1 bar, W1, W1 bar, or something like that. I don't have to necessarily match Z1 with W1. So that's the level of generality of this thing. But once, if they actually matched, so if somehow the angles match, then you can actually find a global ideal. And I can again go to forms and then start looking into forms like this, d log r and d theta. Locally, they would look like that. And these guys again are like just well-defined Lie algebroid forms. They look singular if you are thinking of them in terms of forms on the manifold, but they're just like, this is just trivialization, local trivialization of the dual of the Lie algebroid. Okay, so the idea of introducing these manifolds and these divisors and talk about vector fields tangent to the submanifold or preserving ideals and so on, is that somehow out of this, we produce a new object for which these things that otherwise would look singular are actually well-defined, and I can do differential geometry with them without saying that I'm doing formal computations. So they are actually well-defined objects. Okay?
In the previous case, in the purely holomorphic setup, why do you also consider the partial set bars?
You don't have to. So I think originally, if you just do holomorphic geometry, you just look at the the sheaf of holomorphic vector fields which preserve the ideal generated by Z1, and that would be just the holomorphic analog of the B-tangent bundle, and then you get the holomorphic log tangent bundle, which you can do. So you get like it's also a Lie algebroid, it's a holomorphic Lie algebroid. It's something that's allowed. It just turns out that you can also look just at these smooth vector fields which preserve that ideal, and then you get like this lack of symmetry happening with that one bar appearing, which is also Lie algebroid. So it's like you get the log holomorphic plus T01.
Okay.
So these are like different. At the moment, I would not say there is a correct thing to do. It's just things you can do. And similar to the previous cases, it also works if D has self-intersections, transverse self-intersections. So if D, instead of being just a smooth submanifold of codimension 2, it was locally cut out by Z1 equals to Z1 times Z2 times Z3 equals to 0, then you can repeat the whole story again. And these Z1, Z2, Z3 just have to be local coordinates, local functions, as long as when you kind of try to pick another patch of your divisor, of your D, the ideals should match. So like Z1 doesn't have to be mapped into the W1, but if I look at Z1 equals to 0 and compare if W1 equals to 0, they should give me the same sort of ideal, except that since here I'm not looking at Z1, but R squared, like norm of Z1 squared, that's the condition. Norm of Z1 squared should give me the same ideal as norm of W1 squared. And then I'm game. I can find this Lie algebroid, and you can see that this Lie algebroid already has like something interesting, which is that like if we are looking at vector fields which preserve say R squared, so like the other coordinates are a bit just going along for the ride. So I'll just focus on the first two. So what I'm looking at here is like vector fields on C, which preserve R squared, and dd theta, which would be a rotation on C, preserves R squared, and actually even extends to the origin as a non-vanishing vector field. So even though the action of the circle on C has a fixed point at the origin, which is a bit of what I'm interested in eventually, when I start looking at it from the Lie algebroid point of view, the infinitesimal generator does not vanish even at the origin. So that's like something that the introducing the algebroids allows you to do. It gives you non-vanishing infinitesimal generators even at the fixed points. So there's a relation between all this Lie algebroid that I just introduced. So from complex log to elliptic log, so this last two, you kind of just if you have an ideal, so if you had an ideal, this guy's generated by so here we have an ideal generated by Z, and then you just take Z times Z bar and you get an elliptic one, you get an ideal. That's what you use to define the log guys. And to go backwards, if you have Z times Z bar, you have to have like a systematic way to decide which one is the Z and which one is the Z bar, so don't mix them up as you go through patches. And that boils down to having a co-orientation. So if you have a submanifold and a co-orientation, you can go backwards, and every elliptic with co-orientable D comes from a complex log, and every choice of co-orientation gives you a choice of complex log that gives it. So like the elliptic and the complex are not very far from each other. And the difference is just this: you need to choose a co-orientation for the codimension to stratum. Even if you have like self-intersections, the only relevant thing is really the co-orientation for each one of the submanifolds that is self-intersecting. There's no like the presence of self-intersections does not add anything new, but every submanifold gives you like a choice. So for example, if I had just a single submanifold, there would be two choices of a complex log that gives me the same elliptic. But if I look at CP2, for example, with three lines that intersect, I have three places, three choices of co-orientations, one for each line. So I have in principle 8 different elliptic, 8 different complex log tangent bundles that once I kind of tensor with the dual, the bar, give me the same elliptic tangent bundle. So there is like a multiplicity going on. Is that clear? Like it's just to go from elliptic back to complex, you have to choose a Z. And every time you have different branches coming in. So for each branch, I have to choose which one is I'll declare to be the Z and which one is going to be the Z bar. So I have two choices for each one of the submanifolds. And if I have three submanifolds, I have two choices here, two choices here, two choices here, and then I end up with 8. Okay. Does that make some sense?
Yep.
To elliptic to real log. So the first one, we do that via submersions, and that's the kind of thing that we are interested in the context of circle actions with fixed points, because the model here is really the map going from the complex numbers. It's the positive real numbers, mapping Z to the norm of Z squared. So even though this map, as a differentiable map, has a singular derivative at 0 because of this quadratic polynomial, the derivative vanishes. When I look at what it's doing from the point of view of elliptic tangent bundle here, with C and the origin being the divisor, and R plus being as a manifold with boundary, it actually is just a submersion. So the only algebroids, the induced map has constant rank. So the vector field RDDR here goes to the vector field RDDR here, or maybe 2 times RDDR. So the underlying map between manifolds has 0 derivative, but when I lift the algebroids, it has constant rank everywhere. So it's like a submersion. So like that's the kind of new feature, the advantage you get from having these Lie algebroids. They in this case, they're simplifying, they are making maps that before looked singular, they desingularizing maps in some formal way. If you have seen maybe some talk about, say, Poisson structures and integration of Poisson structures, that's not an uncommon idea, that you have a Poisson structure whose behavior can be quite different from point to point because it's a non-homogeneous type of structure, and try to remove that kind of non-homogeneity by putting all in a map. So you create the symplectic groupoid where the structure is really homogeneous, and all the singular behavior is in the map from the groupoid down to the manifold again. So this is a very much simplified version of a phenomenon like that. I'm putting this complication on the Lie algebroids, and then the map becomes simple when it's seen as a map between Lie algebroids. And you can repeat that also, like as I kept on mentioning, manifolds with corners also work. So if I pick CK with the coordinate planes being the divisors, and RK plus, again, is a manifold with corners, and all I do is like the rotation in all the different coordinate planes. So here is just Z1 mapping to the normal Z1 squared, and ZK mapping to the normal ZK squared. That's also a submersion of Lie algebra. It's just a product of this first example many times. So what this elliptic and log real tangent bundle are doing for me are allowing to write down quotient maps that would happen in the context of, say, the first one here is for a circle action, and this one would be the kind of thing you can have for a TK action, for torus action. Write down a quotient map with fixed, even though the action has fixed points, but the quotient map now looks like a submersion when you see from the Lie algebroid point of view. And with that out of the way, let me tell you something about the amazing hyperkähler structure of CP2. And I have no idea if you guys know about this, but like CP2 is just not hyperkähler, can't be. But now we start putting these divisors, we change the tangent space. So you can start considering different types of structures on these spaces. So for the divisor I've been talking about, so the 3 lines, the Z1 equals to 0, Z2 equals to 0, and the line at infinity, so that forms this divisor structure on CP2. And I can start asking myself, does it have a symplectic structure on the elliptic tangent bundle? Can I write an elliptic form which is closed and non-degenerate at every point from the elliptic point of view? Can I write down a complex structure compatible with that? The answer is yes, it has all of that. So I can actually write down a trivialization in affine coordinates for the log tangent bundle. So here the Z3 coordinates is missing because it's the line at infinity. The divisor is given by the Z1 equals to 0 and Z2 equals to 0. So I have d log Z1, d log Z2, d log Z1 bar, d log Z2 bar as generators of the elliptic divisor. If I also change coordinates, I would see that d log Z1 in the next coordinate would become something like minus d log W2, and d log z2 becomes d log w1, d log w2. So the point of looking at this change of coordinates is that you see that the one forms d log z1, d log z2 are closed. They are globally non-zero in the first affine chart. And when I look at what's happening in the next chart, they turn into these new guys here, which are also closed, because being closed is a closed condition, but they are also closed and remain independent. So in fact, the affine one form d log z1 and the affine one form d log z2, they are defined everywhere. They are closed as Lie algebroid forms, and they give a frame, a global frame for this Lie algebroid. So the tangent space of CP2 with this log structure, the elliptic tangent bundle, is not only trivial, but is trivialized. The cotangent bundle is trivialized by closed forms. So it's like you should not think of CP2. It behaves much more like a torus, right? Which means that also if you want to put structures here, it's as simple as putting structures on the torus. So I can just write down, for example, omega 1 over 2i d log z1, d log z1 bar plus d log z2, d log z2 bar. And that's a global non-degenerate closed form on CP2 with this elliptic divisor. I can similarly write this expression here for the holomorphic volume form. And I see that with this structure, CP2 is actually Calabi-Yau. So that's one of the features that you get once you start introducing these divisors, that the notion of what it means to be Calabi-Yau changed because of the introduction of the divisor. So kind of looking for divisors which are compatible with you're looking for Calabi-Yau structures compatible with the divisor. So that takes the divisor into account. So now I can tell you a little now that you have like we have introduced the log tangent spaces, and I'm kind of have been trying to tell you that these log tangent spaces make the action look simpler. I can finally go and tell you a little bit about how it actually makes the action look simpler. So it's not true that's going to make every torus action look simpler. It's only very specific ones. And here we have this notion of being standard. So the idea is that if I have a circle, torus acting on a manifold, for the action to be simple, it should rotate a few coordinates. So this is the manifold. So the manifold has some circle directions, some CK directions, and RM. And it's allowed to rotate the first so many directions. So everything that, like the first few circles rotate the first few circles, the next few circles would rotate this complex planes, but really like each one of the coordinates being rotated individually, and the RM is just going along for the ride. So like it's a very simple torus action because it's essentially saying that it's made of one-dimensional pieces. I can either have circles rotating circles or circles rotating copies of C and a bunch of copies of R going along for the ride. So I don't know how often you guys think of torus actions, but one famous type of example is that you can have a circle action on R4 whose quotient is just R3. So just fix the origin and the quotient is R3. So that type of action is not included here. So this is like, in terms of torus actions, this would be like the simplest ones. It really is like made of either circle, like it's one-dimensional pieces. And then the question is like, can I tell when a torus action is a standard? Like, if you give me a torus action, how can I decide if it has this shape here? If it's a circle action, it's quite simple. So if you give me a circle action on a manifold, I have to just look at whenever I don't have a fixed point, then I'm fine, because then I would use this factor here to just say I'm just rotating all the orbits around that thing, and that's the end. If I have a fixed point, then I can linearize. And what I'm asking here is that in the linearization, there is one direction that's being rotated by the circle, and the transverse directions are all kept fixed. So I have like one complex direction which rotates, and the rest is kept fixed. So it's something that in principle, I can just write down the linearization of the action, so like computing a derivative, and I can figure out if the action is standard or not just by looking at what's happening at the fixed points. So for circle actions, it's okay. Once you have torus actions of intermediate dimension, it becomes quite a bit trickier because you start having to look at like have an action with like start having weights for the action. And you have to start looking into minors and make sure that the minors have the correct behavior. So if it's like not one dimension or not all the way to half dimension, it's kind of annoying. But if you have an effective torus action of Tn on a manifold of dimension 2n, then that action is a standard. So if you have something like I would like to say toric manifold, except the toric manifold has been taken up by symplectic geometers. And then I guess the name is an effective Tn action on a manifold of dimension 2n. But that's the picture. Like CP2, that's the example I have been going on back to many times, is one example of such a manifold with a T2 action. So a 4 manifold with a T2 action, which is effective. Another example would be S2 times S2. And one thing to keep in mind here maybe is that the torus action is like having a torus action is not connected at all to orientations on manifolds. So T2 acts on CP2, it acts just as well on CP2 bar. Like there's no difference there because like there's no compatibility, like it's all orientation preserving no matter which orientation you pick. There's no relation between torus actions and orientations on manifolds.
So, sorry, do you assume the manifold to be symplectic or something?
No, I don't. No, so that's what I mean. Like CP2 bar is not symplectic. I just want to have a torus action on a manifold. You can always linearize a torus action around fixed points, and if you have this behavior, like the dimension is half of the dimension of the manifold, plus the thing that is the action is effective. So you do have like a connected manifold, and some orbits are the full torus. Then automatically you get the that it will have to rotate. If you have a fixed point, it automatically has to rotate, and from fixed points onwards, you can just go on and get.
So you assume to have at least one fixed point or something?
No, I don't. No, having fixed points is not necessary. I think if you have any point with isotropy, you can already run the argument. Because what it relies is just that once you have a point with isotropy and you try to linearize the nearby, there'll be nearby points whose orbit is the full Tn.
Okay.
So it's not so much about having the fixed point, but having a dense set of points whose orbit is Tn. So as long as the manifold is connected, you're good. So this is like the backward. So I have been saying how if you have an elliptic divisor, somehow it's kind of well suited for torus actions, because it was precisely the situation that the quotient map would become a submersion if I had chosen everything quite well. But the fact that if you have a torus action, a standard torus action, then I can actually use the fixed point set to define the divisor, and then I get this picture that I was describing before. So before I was doing a bit backwards in that I would say, give me a manifold, give me a divisor, then I define the elliptic tangent bundle, and somehow in a few examples I argued that if the manifold was C or C2 or whatever with a specific torus action, then I was getting this nice behavior that the quotient map was a submersion. But in fact, that happens every time you have a standard action. So, but then it's like, it's not that I pick a manifold and pick a divisor, that's the action determines that divisor for me. When I start looking at the points of isotropy, that should be the divisor. And then the action for that choice of divisor will lift to an infinitesimal action, which is in fact an immersion to the elliptic tangent bundle, and therefore the quotient map is a submersion to the B tangent bundle of the quotient. So you get the quotients are going to be a manifold with corners, and the quotient map is a submersion. So like this is like the infinitesimal version of having a free action. So the infinitesimal generators actually give me like an independent set on the Lie algebroid, and the quotient map is just relating the elliptic tangent bundle upstairs with the B tangent bundle downstairs. And this is just like, as long as I have one of these standard actions, you can so you put by hand the compatible divisors on the manifold. That's the idea. So the torus action dictates natural divisors that you should use. Okay. You have a question, Mario? No? Okay. And now that we have this notion of having like an infinitesimal action, for example, we got ourselves our immersion, we can try to define a connection, because connection normally is just like a splitting. So you tell me which ones, like how to go backwards, and the kernel of that would be the horizontal space. And that's precisely what we do. So if you give me a standard torus action on a manifold, a connection is just a, so I get this immersion of the Lie algebra, the trivial bundle into the elliptic tangent bundle, and the connection just does the reverse. It's just an inverse, it's a splitting to that. And the derivative of the connection, which is going to be in principle just an elliptic form. So it's not necessarily an outright smooth form on the manifold, but it's going to be an elliptic smooth to form. So it has d log components, d theta components, that kind of thing. But that one is going to be the curvature of that particular connection. Now, one thing that happens that because these actions are like, I require them to have very specific forms near the divisor. If you give me one connection which has curvature, which turns out to be a log form, so it's not a smooth form on the manifold, I can always change it so that it becomes, so I have a different connection with different curvature, which is a smooth form on the manifold. So that's like one of the outputs of this. That's if you have a standard torus action on a manifold, I can actually pick a connection whose curvature is just a bona fide smooth two form on the quotient space. So for the CP2, I'd get like a bona fide closed two form on the triangle, which is the base of that projection. But then you can already imagine what's going on here. That for CP2, the whole cotangent bundle was trivialized by closed forms. So the thetas, I can choose them to be closed. Like it puts that one in polar coordinates, you get the theta one, and use that as a connection. So it's already closed, and the curvature is going to be 0. So if you never heard of what the curvature of CP2 seeing as a principal T2 bundle was, is because the curvature is 0 and nobody talked about 0 too much. But that's like, there is at least like a general notion of curvature, which turns out to vanish in that case. And that allows us, like, now that if I think what happened with the T-duality for Balknach, Epsling, and Matai, we had to do this thing. If you give me a tree form, I use the tree form to produce a curvature class, and I use the curvature class to change the tree form. So I already have like the curvature class, which is nice and smooth, and I can try already to do this flip, just like they did. And then we kind of let to do T-duality fixed points. Now we have all the tools to extend the framework to fixed points. And that's what we have here. So first is the definition, what it means for things to be T-dual. So now things should be bundles over a manifold with corners. So that's B del B is supposed to be a manifold with corners. And upstairs you have to give me the bundle where the torus is acting, the corresponding elliptic divisor. So you have the D, which has to be the compatible one to the torus action, and a closed three-form H. So if you give me 2 of those, and there's some compatibility condition that I'm not writing here. The relevant part is that I would like to have a elliptic 2 form for which trivializes this difference of fluxes. So df should be h minus h tilde, and this thing here should be non-degenerate. And the compatibility condition is just about how the divisors interact with each other, especially in case I don't pick the divisor that comes from the boundary downstairs.
Can you recall what was elliptic log? Sorry, I forgot.
Mm-hmm. The elliptic is this one that has like happens along a codimension 2 submanifold and it's real. So it has RD log R and DD theta. So sorry, the vector fields are RDDR and DD theta, and the forms are D log R and D theta, and it's the real vector bundle. So in this whole picture here, the one that doesn't really appear much is the one that you asked about, like the holomorphic tangent bundle and the holomorphic with dz. So that one in the middle doesn't appear so much. And the story is really about going for an elliptic with something in codimension 2 upstairs, maybe self-crossings, to be on the base, which is for manifolds with corners. So if I have this situation here in which, like, and here I'm kind of not calling too much attention, but this space here is not a smooth manifold. Technically, to start talking about forms here, I should describe what they are, because the charts here are not based on charts on our end, but like cones on tori. So if you start thinking of what the pre-image of a vertex, for example, looks like, here it's going to be like a cone on a K torus or 2K torus. But it's one of the things that it's not a smooth manifold, but it still has a so to speak, smooth in the elliptic sense. It has like a nice elliptic tangent bundle, and you can actually talk about forms and everything. And then you can kind of repeat the conditions you had for T-duality, which is just asking that df gives you the difference between h and h tilde, and that this df is non-degenerate in the infinitesimal generators, which embed nicely in the elliptic tangent bundle. Okay. So the first result that we have here is existence. So like I already am happy that we have a definition, but are there T-duals? So if you give me a principal TK bundle, like that one, so I have here the bundle, I have this the ideal that defines the elliptic divisor compatible, so that's compatibility with the torus action, which would be the case, for example, if you pick the divisor that's determined by the torus action, and you give me a tree form, then I can actually produce T-dual if the same sort of condition that you'd have in the usual T-duality case. So as long as H has only one leg along the fibers, I can already do T-duality. And one thing that is different, like here I have existence, so the way to produce this T-dual is by a result of Heffliger and Salem that describes TK manifolds. So they have something like, topologically, they have something like Chern classes that kind of fully describe these manifolds. And there's an equivalence between, it's similar to what I have for if I had a circle bundle, I would say that every circle bundle over a certain manifold is going to be equivalent to degree 2 integral classes over the base. So here they have a similar statement. Every circle bundle with fixed points over some base is going to be in the space of circle bundles over base is going to be in correspondence with degree 2 cohomology classes over that base, which is now some sort of singular space. But that's only true if you require that the two circle bundles they're relating to always have the same local model near the fixed point. So that's the locally equivalent part of it. So if you start playing around with that, you can get more spaces because you can have things which are not locally equivalent as well. So this really, in this construction, you construct things for which whenever you have a fixed point on E and one in E tilde, and you try to look at what the torus action looks like, in the appropriate coordinates, it looks the same. So that's not something that it has to be. We just have something that we put there by hand to show that these T-duals exist. Okay. So I guess like there is not a precise analog with the original T-duality picture. The closest that I can get to analogy is that when they were doing T-duality the first time around, they could choose a connection form. So they could pick the bundle. They chose to use the one whose Chern class was C tilde. If they had picked the one whose Chern class was 2 times C tilde, they would also have got a T-dual. So like that's a choice that they made. And here the presence of fixed points introduces a new place where one can make choices. And to prove existence, the result we use is like there exists one which is locally equivalent. So the torus actions on E and E tilde would look very similar in neighborhood would look the same in neighborhood of fixed points. And whenever you have T-dual spaces, which happens with, like, for example, here you have existence, you have the definition, you have the existence result, then you get an isomorphism of current algebroids. But then which current algebroids should I be talking about? Like the original one was nice because it was T plus T star. That's where generalized complex structures lived, and we were all happy. Now it's slightly different because the correct algebroid is the one that is compatible with the action in fixed points. So it's not T plus T star, it's this elliptic tangent bundle. So what I'm getting is that the if I look at the invariant sections of the elliptic tangent bundle, I do get an isomorphism of current algebroids from AID plus AID star to this other guy here. And like essentially the brackets is just, like looks the same like the current brackets. Every tree form on the manifold is also tree form on the elliptic tangent bundle. So the twist is the same, like as you would have before. But the type of objects that you map from here to here are this singular, like the d log going to something, d theta is going to something. So that's the kind of isomorphism you get. So you don't get like outright an isomorphism of t plus t star. And then one thing that's interesting to see is that if the radius inversion here just corresponds to like a change of sign. So it's not it is allowed. You don't get something singular on this context. So whatever it's worth, like I think if you wanted to see T-duality as maps of T plus T star, then you might be disappointed. But these guys here, they look like the tangent space outside of D. So if I remove D, I'm just looking at the tangent space. If I remove D, this thing becomes the cotangent space. So in the complement of D is T plus T star, and you're just doing T-duality as you use it to, flipping tangent in cotangent directions. What you're observing is that if instead of using vectors and covectors, you start allowing these singular generators, then the map extends to the divisor, and you don't have to look at non-compact manifolds. So the sphere doesn't have to become this weird cylinder. It just remains the sphere. So the sphere goes to the sphere as T-duals. But all your tensors now should live on this elliptic tangent bundle instead of T plus T star. So like the hyperkähler structure of CP2 will have a T-dual as well, but not the standard one. The Fubini study will not work. So that's the moment when I think I may have taken a tangent and I have like done a whole bunch of mathematics based on like ideas from physics and thinking like it's so peaceful and quiet here and I'm going to win the race. And whether or not this really has relevance to physics, like, or what kind of relevance it should have, it's to be discovered. But one of the things is that my manifolds have distinguished divisors on them. So ideally, if you're going to do any physics in this context, you should have Riemann surfaces with distinguished divisors on them as well. So it should not just be like picking. If you have a Riemann surface and you want to map to a manifold which has an elliptic tangent space, the Riemann surface is not going to touch the divisor, and you might want to have removed it and work on the open manifold. If you start allowing for your surfaces on the sigma model to have distinguished circles or distinguished points, then we are talking. Then it would make sense to have maps which would have to map the circles or these points to the divisor, and then we can have probably more interesting behavior. But like mathematically, that makes sense. If physics will be justified or not, I don't know. Okay. You're looking very pensive there, Marco. Mario. Jesus, man. Yeah.
Oh, go ahead.
Okay, no, sorry. There's more. Sorry. So let's
okay.
start. It's just that you're looking like you want to ask a question. I
was thinking, but I can ask at the end about whether this covers this case of the focus singularity example. Like
right. Okay. So yes, I think that's right now, because I have torus actions instead of like R2 actions. I do not get focus singularities. That's
okay.
typically something that happens in semi-toric systems, and yeah, so like that's not well suited for T-duality as we are doing here. I really need to have torus actions, not RK actions.
Okay.
So let's go here. The example of CP2, we have a torus action in CP2. It has the triangle as quotient space. All the other torus actions on CP2, which are locally equivalent to this one, are classified by H2 of the triangle, but the triangle is contractible. So and we saw the curvature for that particular connection vanishes anyway. So like not only I have so there is no curvature to switch with anything, and also there is no H3 in CP2 either. So like I don't have my torus doesn't have curvatures to switch to become a flux, and CP2 also doesn't have a flux to become a curvature. So in fact, I cannot really get away from CP2. So CP2 is self-dual, and that's more or less the end of it. And that's because I'm like in this part here, I'm requiring the tree form to be actually a genuine tree form on CP2. Earlier I mentioned that from the log tangent bundle, CP2 feels a bit like a torus, but if you want to do the original tree form coming from physics, it's typically a real tree form on the underlying manifold. So even though CP2 is like a torus, the things that would create degree 3 cohomology in the torus, they're all singular, and they would not come from an H flux from physics. So under these restrictions, I get the CP2 self-dual, and that's the best I can do. And because that was my main example, you might be wondering if we were sitting here for 1 hour for that. But maybe I can just mention one thing, that for H equals to 0, that's the case for CP2, so there's no curvature or anything to turn around, right? And T-duality does not see orientation, so I could pick theta or minus theta. T-duality is the same thing. So because of that, I can pick I can actually make CP2 and CP2 bar, and here should are dual, not self-dual, are dual. I can get a T-duality between CP2 and CP2 bar, which is like similar to saying, it's just that it feels more trivial. But if I say like S1 is T-dual to S1, if I do both S1s this way, or if I do like that as well, they are, in both cases, they are T-dual to each other. The T-duality doesn't see orientation. And you might wonder, like, what's the deal with that? And the idea is that, like, once you start putting structures on these spaces, the orientation starts to become important, because the structures are sensitive. Like often the structure itself determines an orientation, and you cannot get like a complex structure on CP2 that has the opposite orientation. So CP2 is a complex manifold we love. CP2 bar is not. There's no complex structure on CP2 with the reverse orientation. There's no symplectic structure on CP2 with the reverse orientation. So even though these two manifolds that are dual to each other, one of them has a rich geometry and the other one has not, then yet I can transport structures from one to the other. So once I start looking for things which are more compatible with the fixed point set, like the hyperkähler structure on CP2, I can send to the other CP2 bar, and now I get a hyperkähler structure on CP2 bar, so hyperkähler structure with the opposite orientation. So there's something interesting going on with CP2 and CP2 bar in this issue of orientation that actually is geometrically interesting, even though it seems a bit silly in this example. Another thing that does not see fixed points is blowing up. So to blow up a point, I think one thing that we are familiar with is that if you have a complex manifold, I can blow up a point in a complex manifold. And to do that blow up, I need to know a bit like holomorphic charts in a neighborhood of a point. But technically, I need to know a lot less than that. I don't need to know Z1, Z2, Zn. I just know the ideal generated by this guy. So I need to know the ideal generated by Z1, Z2, Zn. Now, if I set up having Z1, Z2, Zn, I had Z1 bar, Z2 bar, Zn bar, I could also do the blow up. So putting bars in all the coordinates still gives me a blow up. Except that in one case, I'll get like, say, if I'm in 2 dimensions, if I blow up a point, I get connected some CP2 bar. And if I had done the opposite orientation, say Z1, Z2 bar, so that's one of the possibilities. I flipped one of the Zs, I get the opposite orientation. Then the blow up would correspond to connected sum with just CP2. And the blow up doesn't see orientation. And if you blow up fixed points, it's actually compatible with circle actions. So this whole elliptic tangent bundle thing, if you blow up a point and you see what happens in the elliptic tangent bundle, it gives you something that's as close to being diffeomorphic without being. So you can actually blow up with independent orientations. It doesn't have to have an underlying complex structure available. And then you can start adding CP2s or CP2 bars depending on which one you like. And all these guys here will be dual to each other as long as I have like the same total number of CP2s and CP2 bars. So like the blow up process is blind to orientation. I can make choices, and T-duality will be like, they'll all be T-dual as long as I kind of added the same number of copies. And that's just because then once I add the same number of copies, all these guys here will have base space under the T2 action polygon with n plus 2 sides. So I have here a collection of spaces which are all T-dual, and one weird thing about this example is that there is no degree 3 cohomology class to talk about. The degree 3 cohomology of the spaces is still 0. If I start looking at the tangent space, it's still trivial with closed form, so there's no curvature, and yet I'm getting topology change. They're all distinct topological manifolds. And what the source of this topology change is that they have locally non-equivalent T2 actions. So that's like a new source of non-uniqueness for T-duality. So this is something like you can just work out, because like these are simple manifolds, and the blow-up process is also a simple process. It's something you can work out and see the difference in the torus actions on all of them, and see that that's where the topology change is coming from. But that's a new source of topology change. Before, like the first time around, if back in 2000s, you're all surprised that the 3 form could come in and turn into the curvature of the manifold. And now the presence of fixed points can also determine topology change, or like several T-duals on the other side. And then there's the lifting question, which I'll very briefly touch, because I'm sure I have been over time already by a whole chunk. I'm sorry for that. So the lifting question is very simple. Like originally, we're often interested in structures on the manifold. So you just have like you have M, look at T plus T star of M, and I'd like to put some structure there, complex, symplectic, or something. Now, it may quite well be that you have a structure there that actually you can lift to the elliptic tangent bundle in a very natural way. Sometimes it's so natural that you don't even see you're doing it. But then you do T-duality and you get, again, a structure in the elliptic tangent bundle on the other side. And there might be much more clear that you are asking yourself a lifting question. So let me just try to give an example here. If we start with a complex manifold and a complex submanifold, then this elliptic tangent bundle just inherits a complex structure, because what Mario was asking in the beginning, like if I had just done the elliptic tangent bundle, I'd have like Z, Z, Z2, Z3. So like it's so natural that you might start talking about this log geometry as if it just belongs to the complex manifold M. You might not even like think twice about it. But now you have this complex structure lifted to the elliptic tangent bundle. I can do T-duality to that structure and see what it lands. And when I go to the T-dual, it might be quite more clear, a lot more clear that there is something going on, because the T-dual might not even be a complex manifold. So suddenly I have all these D-logs and the theta's and so on. So I'm very clearly dealing with something somewhat singular, and it's not coming from an underlying complex geometry. And you might wonder, well, but does it descend? Like, is it also the lift of something from the manifold? And the answer is that only for a specific case. So like for very specific choices of this 2-form F, it may quite well happen that the T-dual thing also is the lift of something from the manifold. So one example we had is that if for specific choices, you can do T-duality on the complex structure and get one of these things that we call stable generalized complex structures as is the T-dual. So the stable generalized complex structure is one that when you lift to the elliptic tangent bundle, it becomes symplectic. So there's actual work to be done in that case, while in the complex case, we lift to the elliptic tangent bundle, get something complex and don't think twice about it. But there is this question, like I'm wary to say that the complex structure on CP2 is T-dual to the elliptic symplectic structure on CP2, because the ones that are really T-dual are the ones on the elliptic tangent bundle. And it just happens that somehow they are related by this lifting question. Once you have a lift, it's unique. But the upstairs is where the whole magic's happening, where you have all the symmetries that you'd like to have. So one thing that's like is currently work in progress, but it's just a word of warning that a lot of people do mirror symmetry on funnels. So that's like a area of research. Mark Ross has a lot of papers on that, and a whole bunch of people working for him. So if you start Googling about Loyenga pairs and mirror symmetry for log calabi-Yau, that kind of thing. You see there's a lot of work going on there. And when I start seeing log calabi-Yau, I think that's like the differential framework that hopefully would describe log calabi-Yau. Currently, they are only done in algebraic context. Would be this one that I'm describing here. Hopefully, what you're doing here is a differential framework for understanding the geometry of funnels and log calabi-Yau. And there we kind of the mirror symmetry of the complex side is frequently like lifts, like you don't care. It's like it's too obvious. But somehow the idea is that there is an underlying lifting question going on. And if you want to understand what happens in the mirror, it's good to understand that you did a lift. And that on the other side, you are going to get also a lifted structure. And whether or not it comes from something just defined on the original manifold is typically not the case. And it is a genuine question. And with that, that was actually the end of what I had to say. Thank you guys for sticking through all this presentation.
Yeah, thanks, Gil. Are there more questions? I sort of wondered if you could just maybe say a little bit more about the metric side. So I guess so you do have this notion of T-duality now for fixed points. So for instance, like this like hyperkähler structure on CP2, I imagine naturally maps to itself under this.
Yeah, so like that one was flat, right? So yeah. the things that, let's see here if I can go back to the Buscher rules, is just that once you put the correct generators, so like the theta here was supposed to be something that pairs one with the circle, like the infinitesimal generator. And then you have, if you have something which, a circle that's collapsing, you'd have an R² type of coefficient here. Mm-hmm. But if you want the correct connection here would be, so what do I want to say? That's like when I put an R² here, and I think of it as an elliptic metric, having an R² here is no good, is not a metric anymore. Sure. Because theta is just a genuine thing which does not vanish even at the divisor. So if I put an R² here in front and I see what happens when I'm thinking of it as an elliptic metric, then I'm getting something which becomes degenerate over the divisor. So then I have to kind of change the type of coefficients I allow these metrics to have. So the metrics automatically should have some sort of singular behavior as I approach the divisor. And for that particular thing, what, as I mentioned, was like given by closed forms. I'm sorry to skip over this quickly. Let's try to see if I can find the example. Yes, like the metric is like the whole thing is given by these closed forms: d logs at 1, d logs at 2. So the metric is really like d log r1 squared plus d log r2 squared plus d theta squared plus d theta 2 squared. So all this is, it really is like it's from once you kind of translate it into the elliptic tangent bundle, it looks quite uninteresting. And indeed the metric, because it's just like a product, it really kind of self-dual. If you make all the choices, that would be the usual ones. So you're not going to be changing the metric on the hyperkähler metric on CP2, but it's like doing T-duality on the torus. You don't change the torus too much.
Yeah. So somehow a Buscher rule is the same, I guess. It's just for a slightly different class of objects. Or
exactly. Yeah, exactly. So the Buscher rules, they have to stay the same, right? Because if you remove the divisor, just back in the original case. And indeed, the trick is just that now the tensors that you're transporting are different. Mm-hmm. And we're kind of identifying a new class of tensors that gets preserved by T-duality, and for which it actually makes sense to talk about structures on this place. Like the tensors are not just like, I could have probably done T-duality without having introduced the elliptic tangent bundle, just by saying, look, I observed that if I allow myself to write d theta and d log r with like smooth coefficients and everything goes well, but like by introducing the elliptic tangent bundle, you're kind of observing like what's the space where these things live. And then you get the isomorphism of current algebroids that you'd not have got otherwise, which allows you to actually transport structures, including things that are happening at the divisor. And I find that from that point of view, at least, it's interesting to see this thing of the complex structure being T-dual to a genuine generalized complex structure. with type change along the divisor.
Right.
If you know, like that's a rare phenomenon. Typically, it's just going to be a generalized complex structure on the elliptic tangent bundle that does not have to come from something from the base.
Okay. Okay. Yeah, thank you.
Okay.
Okay. Can you
Mhm.
understand this Auguri buffer metric, which can be regarded as a H1 bundle over some opening R3, but the total space has a fixed point? Is it possible to understand this in your picture? So can you T-dualize in your sense?
So it's say again, symmetric where?
Yeah, so there is this paper, the thing I know, this paper by Gross and Wilson, where they describe like some approximation to Keller-Ricci flat metrics on elliptic K3 surfaces. And the model around a singular fiber is this Auguri buffer metric, which is like C2 minus the origin, fibering over R3 minus something, and then actually the metric extends to the full C2.
Right. Yeah.
And you have a natural S1 action, which is just the circle action on one of the C factors and the inverse circle action on the other factor. And then
I think that like I didn't look into that one, so I have to like I cannot give a precise answer at the moment. But if you're doing like a T-duality on K3, or if trying to in some sort of near symmetry on K3s, you're saying.
Yeah.
Then you like the K3 itself will not have a circle action, and you can try to model neighborhoods of singular fibers. But I think that then it's more like focus. You get a circle action and an R action. You don't get a torus action there, right?
Okay, so it's back to the same thing. Yeah. I was my focus. My question about focus was precisely because of that.
Right. Yeah. So like the T-duality and this, like we have a whole bunch of work on generalized complex structures and fibrations, so on, and how these focus singularities also appear related to generalized complex structures. But it's like we didn't do T-duality for that yet, so that is clearly more complicated because you don't get the circle action. So one of the things with T-duality that allows for it to work is that you can look at invariant tensors. And if you just have K3s, then you shouldn't expect to have the same ability to just push, like send tensors from one side to the other like that. But and the other things that just in terms of fibrations, one thing that works well for generalized complex structures is symplectic fibrations. Although for K3s, typically focus singularity and so on, you're talking about Lagrangian fibrations. So even like the relation to generalized complex geometry in this picture of a semi-toric geometry is a bit lost there. Like they have a lot of fibrations that look similar, but when you start putting structures on these fibrations, the structures are kind of opposite to each other. One case is non-degenerate, and the other one is really fully kills the symplectic structure when it restricts to the fibers. So yeah, like this would be one step further still, because it's like removing the question of invariance to do this kind of duality that you're talking about.
Any others? Any other questions?
Can you say something in this context about the? I mean, can you extend this result about the isomorphism of these twisted cohomologies or K theories to this setup with fixed points?
So I have to. I did not like I did not look into that. The twisted cohomology should still work, but in the context of the Lie algebraic cohomology, just because it's the same, right? So like you pull back to e to the b and push forward. So you should get the isomorphism of twisted cohomologies for the Lie algebraics. I did not think of what a twisted K theory is with Lie algebraics hanging around. Or if we have to replace it by something else.
I see.
It's a good question.
I see. Thanks.
Thank you.
Okay, any others? Okay, well, yeah, let's thank you again. That was very nice.
Thank you guys for staying all the way to the end. Thanks for the invitation.
Yeah, yeah.
It's nice to see you guys.